Hello there, Mr. Sutton here, bringing you this lesson on total distance. In this one, we'll be finding the total distance traveled by a particle, which is a little bit different than its displacement, and we'll also be finding the average velocity of a particle on an interval. For a warm-up, we have a graph representing the velocity in meters per second of some particle moving on the x-axis. We want the net distance and total distance traveled on the interval from 0 to 10. Pause the video, give it a shot. All right, so we're finding area under the curve here. We have a rate of change of position, so we want to find total change in position, or at least that's kind of our starting point. Now, we've got different types of areas that we're going to be adding together. We have two positive areas, and then there's this negative area below the x-axis. When you're doing net distance, the sign of the area matters. So we've got the area of this first triangle. That's going to be a base of 2 times a height of 3 over 2, or 1/2 times 2 times 3. Then we have this trapezoid. We have a base of, 5, a base of 3, so we're adding those, 5 plus 3 over 2, and then we're multiplying by height of 3. Since this is under the x-axis, this is going to be negative area. And then we have this last triangle. We have 3 times 3 over 2 for that one. And then if you wanted to simplify all of this, this is going to be, 3 minus 12 is negative 9, plus 4.5 is negative 4.5 meters. Okay, so how does this differ from total distance? Well, with total distance, the direction that we're going doesn't matter. Like this spot down here where we turned around because we had a negative velocity, we don't care that you were walking the wrong way. All the area is treated as positive. So the only difference between net and total distance is going to be we're going to make this middle term here positive. And then adding all this up now, we still have 3, but this is going to be plus 12 and plus 4.5 for a total of 19.5. For this next example, we have a particle moving along a coordinate line with a velocity function for t greater than or equal to 0 given as follows. This will be 6t squared minus 6t. We want to find the total distance traveled on the interval from 0 to 2. So pause the video and give this a first attempt. Did you end up with an answer of 4? If so, then you made a good try, but you were missing something in between. So whenever they're asking for total distance and you can't see the function, you really do need to check for sign changes in the velocity. So we're going to go ahead and check for those direction changes by setting this thing equal to 0 and solving. We can take out a 6t when we do that, leaving us with t minus 1 inside. So we then have critical values of 0 and 1. Let's go ahead and do a little sign analysis to see what the signs are for our velocity. So 0 we don't have to worry about because we're asking about time greater than or equal to 0. So really it's just 1 we have to check. If we plug in something to the left of 1, like 1/2, that would be a positive times a negative, so negative overall. If we plug in something bigger, like 2, that would be a positive and a positive, so positive overall. So we do have a direction change for our particle because our velocity has different signs at different points along this interval. So how do we deal with this? Well, if we just take the integral of this directly from 0 to 2, we're going to be throwing in some negative distance along with positive distance. And that's not going to tell us the total distance traveled. It's going to tell us the net distance. So to fix this, we need to split up this integral and use absolute value for each piece so that we're making sure all area under the curve counts as positive area. So we're going to have the integral from 0 to 1, because that was our critical value, our sign change value of our velocity, plus the absolute value of the integral from 1 to 2 of the same function. So at this point, let's go ahead and take some antiderivatives. We're going to have this bumping up to third power. Dividing by 3, we have 2t cubed minus, this will be 3t squared. So we're going to evaluate that from 0 to 1 for that first integral. And then from 1 to 2, same antiderivative there for the other integral. Okay, let's go through and split these up. We're plugging 1 and 0 into this expression and subtracting, all inside one big absolute value. And then we're going to plug 1 and 2 inside the same expression and subtract, all inside another absolute value. And we're adding those absolute values together because we were adding them together up here. going through and taking a look at each one of these, we've got, let's see, this 0 stuff is just going to be 0. Over here we've got 2 minus 3, which is negative 1. So the whole first bracket here ends up just being absolute value of negative 1. Next, for this one, we still have negative, actually not negative 1. This is negative 1 over here. Over here we've got 16 minus 12, so that's 4, minus negative 1, so that's a total of 5, and we're adding the absolute value of 5 then to the absolute value of negative 1. So this ends up coming out to 1 plus 5, which is going to be 6. So you were pretty close. You just had the wrong sign on that first distance there. For this next problem, they want us to find the total distance of the particle with this velocity function, and this time they're going to let us use a calculator. All right, well, there's a couple ways to do this. So approach number 1 would be to actually find the direction changes using the calculator, using Desmos, and then split up the integral. Basically just do what we did, only using the integral function on Desmos. Let's take a look at what this looks like on the calculator. So if I go to Desmos and graph this out, we've got v of t equals fraction sine of 9t over t. Ooh, that's kind of wild. Let's look at the interval from pi over 2 to 2 pi. So let's go to my wrench, and let me just move this up so I can see it. I'll make my x-axis go from, we'll just do 0 to 2.5 pi. And we'll make our steps go by pi over 2 so that we can see pretty clearly. So our interval starts here at pi over 2 and ends here at 2 pi. So if you zoom in a bit, I mean, you'll see this thing is, the velocity is changing sign multiple times. That's indicating multiple direction changes. So you would have to find all of these sign changes and then create an integral for every single one of those. So that's a little bit kind of nasty if we're trying to do it this way. Yeah, have fun with that. Another way to do this, instead of worrying about whether each of these areas is negative or positive, if we're allowed to use the calculator, we can just integrate with a single integral, but we're going to put an absolute value around the integrand. So with that little idea in mind, pause the video and see if you can implement what we're talking about here. All right, so here's what I mean. We're going to take the integral from pi over 2 to 2 pi of just v of t, but we're going to put v of t in the absolute value. So we'll have absolute value of v of t dt. And notice that the absolute value is not around the whole integral, it's just this integrand, so that every little change in velocity, every little change in position, I should say, is going to be counted positive. So going back to Desmos and implementing this, we're just doing integral int from pi over 2 to 2 pi of, and now we'll just do the vertical bar to open absolute value, v of t, close the vertical bar, dt, and that comes out to about 0.883 and some change. So there we go, much faster. For this last problem, we have a particle again moving along a coordinate line with this velocity function. We just want to find the average velocity of the particle on this interval. Now, in the past, when we wanted average velocity, we had a distance function, and we were doing the average rate of change of that. This time, we have the function itself that we're trying to find the average of. If only we had a formula for finding average value of functions. I bet that would be helpful here. Pause the video and give it a shot. All right, so using our average value formula on velocity itself, we have 1 over b minus a, so 1 over 9 minus 4, times the integral from 4 to 9 of the thing that we're trying to average, which is just v of t dt. And we just need to go into the calculator and enter all this in. So as always, let's begin by putting the velocity function in here. That's 3t squared minus 18t. And then we'll just do a new entry. We've got 1 over 9 minus 4 times integral from 4 to 9 of v of t dt. And that's coming out to exactly 16. Awesome. So that's it for this one. Thank you for going the distance with me on this lesson. Till next time, Mr. Sutton signing off.